And now for something completely different.
Well, not completely. I mean, it is still me. And it is still chemistry. Everyone needs peanut gallery. But what we're talking about today is different from the other things you've learned, because before what you've learned in this class is things that you had learned before, and we went a little bit deeper. When you hear the word mole, a couple pictures might pop in your mind, maybe a little animal, but that's not what we're talking about. Maybe a spot on the skin, and that's not what we're talking about either. Really, for us, the mole is going to be centered around this chap. And his name was Avogadro. I don't remember his first names, he had several of them. He came up with a number, and that number is going to be really, really important. And that number is what we end up calling the mole. So what I've been saying is that the mole is a number. So let's talk about numbers. So we know about numbers, and we know that when numbers get really big, like say for example 8 billion here, we stop writing all the digits and we just write a word. So we have words that mean numbers. And those numbers, when they're really big, we can do fractions with them, and that's no problem. So it's kind of hard to talk about, say half an egg, but you can have half a dozen. So we can do, when we're talking about larger numbers, we can do fractions of them. And again, you don't need to write this down, but think about what we know as we start moving into the chemistry. If I have a formula, even a complicated one, I can count up the atoms. So I got 3 here, that 2 applies in, and into there. So I add them all up, and I've got 13 atoms. Well, if I start having more of those pieces, 3 of those pieces, each one has 13, so 3 of them would have a total of 39. Well, let's expand that into a bunch. If I had a dozen of them, okay, well, then I know what to do. I take the number that I have and I multiply it by my new package, in this case, dozen. I've got 1,000,000. Okay, well, same thing. I've got a new package full of these things. It's a 1,000,000, so that would contain 13 million atoms. And same thing if I expanded that into the 3,000,000 pieces. Well, that would have 3,000,000. Each million has 13 because each one has 13. So 3,000,000 have 39 million atoms. And what about a bazillion? Well, a bazillion, whatever that number is, it's a word that means a really large number. That would have 13 bazillion atoms. And if I had 3 bazillion, that would give me 39 bazillion atoms. So we just keep expanding that thing. Okay, this you want to know. So this you want to have written down as a definition. And it's much more specific than just a really big number. It's going to be a very specific number. And this is the specific number. Now, you don't really need to write this number down. We're not actually going to use this number. What we're going to use is the result of this number, what it allows us to do. But here's the number, 6.022 times 10 to the 23. Fun to say. It also has a mathematical phrase, and it's a sextillion. It's more important for us to understand what it allows us to do, and we're going to use it to count very, very large numbers of very, very small things. Atoms. Atoms and molecules are extremely small. We cannot count them by individuals. So 1 mole of iron is this many, 6.022 times 10 to the 23. Now this number has a name, and you remember the lad I showed you a few minutes ago, Avogadro. This is called Avogadro's number. I'm not going to use that a whole lot, but it's worthwhile to know what we're talking about. If we keep going keep building on that, a mole of molecules, so a mole of atoms, Avogadro's number. 1 mole of molecules, Avogadro's number. Now within that mole of molecules, I would have each molecule's 3 atoms, so I could build that as well. I'll start counting atoms like I was doing a few minutes ago with that calcium compound. 3 moles of molecules, well, that would be 3 times Avogadro's number. So if this represents 1 mole, just like 12 represents 1 dozen, then 3 moles would be 3 times that number, Avogadro's number. Well, the big thing is we're not going to, and I mentioned this earlier, we're not going to use the number. What we're going to use is the result of it. What we're going to use is what it allows us to do. So the big thing is we're going to use it for counting. Now remember, we can't count individual atoms, so we are going to have to make another connection, and we'll come back in a moment. You don't really need to write this down if you've already started. Sorry, I should have mentioned that earlier, but it's not going to be a problem if you do. But again, this is what it allows us to do with it. So if I give you this question, totally different from atoms and molecules, now you may have said 48, you may have said, and I'm hoping you said 4 dozen. You looked at the package and said, okay, that is a dozen eggs. I've got 4 of them, so that gives me 4 dozen. That's the thing we're going to do with moles. We're going to repackage our moles into a container. It's not going to look like a carton. It's not going to look like anything physical either. But we're going to repackage them and we're going to call them a mole. So, how do we do that? Quite simple actually. We're going to start with something called molar mass. Now we need to keep our terms straight because we've got moles, which is our counting tool. We've got molar mass, which is going to be how heavy one mole is, and then we're also going to work with masses. So we're going to have 3 things that kind of overlap, and that's really where things get a little bit confusing. But the molar mass, by definition, is the mass of 1 mole of substance. Not a bad definition to know, although honestly, if you were to write it down, by the time you go back and look at it later, you'll wonder why you ever needed to write it down, because it's going to become so second nature to you. It's measured in grams per mole, and then our short form is grams per mole. Now, I didn't forget the E back here, and I didn't forget the E here. This is our short form for molar mass, or not our short form for molar mass, that's our short form for the unit, grams per mole. And this is our short form for mole. It's not as short as maybe you could come up with, but that is the accepted short form, and that's the only one we're going to use. We use the numbers from the periodic table, the mass numbers, and this is why that number was so weird, that Avogadro's number, why it was a 6.022 times 10 to the 23. Because what it allows us to do is use the numbers from the periodic table for our masses. So if we take a look at a periodic table, and we remind ourselves where those masses are, they are right below the symbol. And maybe in this case below the name as well. I'm going to zoom in on a few. So one type of question that you might see is, what's the molar mass? And if you don't see that type of question, you will be calculating molar mass all the time. Let's take iron. So I need my periodic table. If you don't have one, I'll show you the picture of it. There's iron. There's the mass number. Now we know that to be the mass of a single atom. But if I had Avogadro's number of atoms, that would be in grams the mass, 55.845 grams if you had a whole mole. So the big thing about mole is that it allows us to use those mass numbers still. What about potassium? Again, look at the periodic table. There's the mass number. If I'm talking about a single atom, that number works. If I'm talking about Avogadro's number, 6.022 times 10 to the 23, that number works. And that's the whole point of the mole. Works also for molecules. So if I build my molecule, so here I've got 1 carbon, I'm going to have a total of 4 hydrogens, and I'll have an oxygen. I guess I've gone from numbers to symbols there, but hydrogen, carbon, oxygen. Here's my mass numbers. Now I'm going to round these numbers off just to make the math look a little bit simpler. And we'll talk about rounding in class, what are sort of our limits for rounding. But my carbon is about 12, my hydrogen is about 1 each, 4 of them, and 16 for oxygen. Add them all up, 32 grams per mole. That's the molar mass. Notice it's capital M, capital M. Little m's have already been claimed by millimeters, and we're not going to use those. Capital M, capital M. How about this one, MgSO4? We probably haven't done the nomenclature of this yet, so I'll just call it as magnesium and sulfur and oxygen compound. And that one is, take the numbers, all right, so 24.3-ish, 32.066 more or less, and I'll round this one off to 16 again and add them all up. Now I had 1 magnesium, 1 sulfur, and 4 oxygens. So I have to multiply that by 4. But just like I did before, add up the numbers. That's my molar mass. So the molar mass of a particular compound is based on the atoms in that compound. And I use the numbers from the periodic table. All right, so hopefully that makes some sense so far, and nothing's really all that crazy yet, right? I mean, we're just taking the numbers from the periodic table. Okay, so if I give you a chemical formula, and I give you the molar mass, the ones we've already seen, I'm going to ask you to calculate the mass of some different number of moles. Okay, so if I had, well, 1 dozen eggs, how much does that weigh? What if I had 4 dozen eggs? Okay, hopefully you're already thinking ahead as to how you would answer that question. It's going to work the same way for moles. So here's my chemical formula. We saw that one before. There's the same molar mass we saw before. What if I had 0.25 moles? Well, I'll give you a moment to figure this out, but if you had 0.25 moles, just like you do with anything else, you would multiply the number of things that you have, the number of packages you have, we're calling the package a mole, times the mass of each package. Okay, so our molar mass is the mass of each package, and I've got 2.5 packages. So multiply it out, 80 grams. You'll notice that my number here is just grams. All I'm doing is calculating the mass, and mathematically on my units I've got moles times grams per mole, put that back, times grams per mole, moles on top, moles on the bottom, canceled out, I'm left with grams. Okay, for this one, same deal. Here's the mass of one package. How about if I had 0.63 packages? And I'd multiply it out. The number of moles, number of packages, times the mass of each package, and I'm left with 75.8 grams. Just to give you a quick little summary, and actually more of a formula rather than a summary, here's what we've been doing. To calculate mass, I take the number of moles times the molar mass. That's kind of a klutzy formula, kind of an awkward one, so we're going to shorten it up. And then we need to keep track of labels and terms. So number of moles, N. Molar mass, capital M, capital M. This one I get from the periodic table. This one I'm going to have to get from the question. This one I'm calculating out. Well, we often do know the mass of something. I mean, I might ask you to put something on the balance and you can measure it out, and you know what the chemical formula is. So now I can calculate from here and the periodic table molar mass, and I've just measured the mass. Well, what do I do with that? I'm going to take the total mass that I'm given, 37.5 grams, divided by the molar mass. And when I do that, I get this. So 37.5 divided by 120.3, 0.31 moles. Now that might be a little bit confusing, so let's kind of take a little bit of a side trip and think about something in a different way. Think about something a little bit more familiar. Let's say that eggs cost this. I don't know if they do, and that doesn't really matter. If I had $13.62, how many eggs could I get? Or how many dozen eggs could I get? Well, I would take the total price that I've got, $13.62, and divide by how much each one costs. And I don't really care what that number is. What I want to do is I want to compare it with the formula that we used a moment ago. So instead of number of dozen, number of moles. Instead of total price, total mass. Instead of cost per dozen, mass per mole. So this is my package, dozen, that's how much it weighs. This is my package, mole, this is how much it weighs. I think I said weighs back here too. Here's my total price, here's my total mass. So we're doing a very, very similar kind of thing. The challenge is not the math. The challenge is the terminology. So if you're getting bogged down thinking this is really difficult math, focus on learning the terminology, learning the terms and the units and stuff, because the math is actually quite simple. Okay, so just to put that as a summary, and not only as in words, but also in a little bit more of a formula that we can shorten up using the same one. So I've got a mass, number of moles again, just using the N, molar mass, which we get in the same way, right from the periodic table. This is an equation triangle. An equation triangle, if you took physics, it might be familiar to you. It's useful anytime we have three terms. So the way it works is I cover up the thing that I'm looking for, and whatever I have left, that's how I arrange the formula. So let's say I'm looking for mass. Well, if I'm looking for mass, I'm going to cover up mass, and I look at my triangle, excuse me, and I have number of moles on the bottom and molar mass on the bottom, and when they're beside each other I'm going to multiply. If I'm looking for number of moles, well then I cover up number of moles, and I've got mass on top, molar mass on the bottom, and then I'm going to treat that as a division. So the triangle is really quite simple, it's quite handy. Okay, you know what's coming. I'm going to leave you with a few questions to try, and we're going to pick those up in class. Here we go. So you might want to pause it. You notice that the formulas get repeated so that you don't have to figure out molar mass every time. Normally what's going to happen in a question is you would see either this or possibly both, but you wouldn't see all three. And yeah, we'll be talking to you in class, and we'll be checking these questions on you. All right, talk to you later.